Okay. So let's try, not that one. Homework 3.3. All right, so this is a steam power plant, ideal Rankine cycle with superheat. I'm given the pressure and temperature at the inlet, mass flow rate. I'm given the condenser pressure, and saturated liquid exits the condenser. That's going to always be the case with an ideal Rankine. It's fed to the pump. The turbine and pump have isentropic efficiencies. Right? So the ET is the efficiency of the turbine, 90%, and then EP, the efficiency of the pump, 90%. So that means there's a rise in entropy in both the turbine and the pump. So what I'll do is do the problem with 100% efficiency and then find my exit state by using the adiabatic efficiencies, or the isentropic efficiencies. So let's see if we can copy that problem back on top here somehow. All right, and I'm going to try and push it off to the side. I don't think I need the text anymore, so we just need these numbers here. Oops. All right, come back. Nice. If I can figure out how to get this. I don't know where it went. It like threw it off somewhere. Come back. Very nice. All right, I'm going to pause this. Okay. Is it recording? I have no idea. Stop recording. I guess it's recording. I don't see any sound though. Hello? Test. I guess it's there. All right. Being interesting report. So, here's another problem with can't remember. Did I describe it on? I did, and then paused it.
Yeah.
It's been so long. Anyway, welcome back. It's been like 10 minutes later. So P1, T1, M1, P2. So let's just draw a quick turbine. Then it reheats, right? Is that what this problem was? It's been so long now. Can't remember. And it goes into a condenser. Goes into a pump. Goes back to our steam generator. I think, or it doesn't even have reheat, does it? I better reread the problem. Oh, with superheat, not reheat. Okay, so this is getting ahead. This problem would be for the next homework set. So this first set's really easy. It doesn't have reheat, it just has superheat is all. The only thing it has is isentropic efficiencies. So TS diagram. So if I label that state 1, state 2, state 3, and state 4, draw a saturation curve. It's superheated, and it expands. Maybe it's saturated liquid, maybe it's liquid vapor mixture. So this doesn't have to be right there on the line. And then state 3, right there. State 4. All right, so state 1 is easy. I know H1 is a function of T1, P1, right? Go to the superheat tables, look it up. That's easy, so superheat table. All right, state 2, I'm going to say, so this is state 1, 2S I'm going to do. I'm going to assume it's isentropic, right? Then the real state 2 we'll have to get. So state 2S says that S2 equals S1, that's my assumption. And then I'm given P2. So my H2S is a function of, P2 and S2. Right? Again, superheat tables to find that. So I know entropy and pressure. Instead of looking on the left column for temperature, I look for entropy, and I'm going to have to interpolate almost always and find enthalpy. Right? Then, but how do I find the real one? Well, the turbine efficiency, which I called ET, is going to be the actual output over the ideal output. So the actual is always going to be less than the ideal, right? So my efficiency is less than 1. So this is 90%. So what is the ideal output? They're both m dot times delta H. So this is H2 minus H1. I don't know if I can move this over anymore, but I'll try. Oh, but my little paper is on the edge of my paper. And this is H2S minus H1. So I've got H1 I already found, H2S I already found, so I solve for H2. So H2 equals the efficiency of the turbine times H2S minus H1, and then, well, that's actually H2, H1, I guess that's a negative number. This is H2S. So plus H1. It's kind of a weird way to write it, but that's all right. So this is a negative number times this, so it's less than H1. H2 is always going to be less than H1 because I'm going to get the actual work. And so this is kind of strange. This is a negative number over a negative number. I really should write it H1 minus H2, inlet minus exit is the work.
Yeah, that's the way it is.
So I just switched those, but it still works with the equation. It's just negative. This is negative of negative. So the negative work over the negative ideal. So it's just kind of strange the way I wrote it. But this equation is still fine.
Ideal is the same as isotropic, right?
Yes. So yeah, if it's adiabatic efficiency, isotropic efficiency, we're talking about the same thing.
And why are you doing negative?
Negative actual, just because I wrote this backwards.
Oh, okay.
I normally write H1 minus H2, but it's still fine because I did them both backwards. So I put H2 minus H1 for both. You can write it H1 minus H2, but the work typically would be equal to m dot times H1 minus H2. So in keeping with that definition, since I wrote H2 minus H1, I just didn't want to erase it and change it. But I end up with the same equation here, right? Just that this is a negative value. So now I have H2, so that's, I think, one of the first things that was asked for. Then, so determine the specific enthalpy at the turbine exit. Oh, the inlet, that was easy. That was H1. We found that in the tables. Determine the specific enthalpy at the condenser exit. So we did this one, the inlet and the exit. Now the condenser exit, that's easy. That's just saturated. So H3 just equals HF at whatever we're given, temperature or pressure. It's P2, right, at P2. And so at 0.008 bar, we go to the saturation tables and we look up HF because it's right on the saturation curve. The next thing that's asked for is determine the power produced, let's see, specific enthalpy at the pump exit. All right, so how do I get that? At the pump exit, right here, there's a number of ways to do it, but the work for the pump, if it's isotropic, is V delta P, so delta H for the pump That's if it's isentropic. The so H4 would equal H3 plus V3 times P4 minus P3. Alright, so which V do I use? Well, it really would be V delta P plus P delta V, but I mean, that would be the definition of delta H, but we're saying that the specific volume doesn't change in the pump because it's incompressible. So P delta V would just be 0. So, and then this is the pressure difference across the pump, P4 minus P3. I can use V4 or V3. The temperature wouldn't change across the pump if it's isentropic. So the specific volume doesn't change. So this is just the inlet specific volume. H3, we already found it's HF at the pressure. So then I can solve for H4. If I wanted to do it that way, yeah, I guess I was asked for the specific enthalpy at the pump exit. The only thing is that's for S. Because I assumed, this equation assumed that it was isentropic. So then how do I find the actual enthalpy? Same way I did before, right? That the efficiency of the pump is equal to EP, that I called it, 0.9. And then that's going to be, now this is kind of the other way. We always put the larger number on the bottom, so the larger number is the actual work. And the ideal work, or the isentropic work, is a smaller number, right? Because ideally you want less work into a pump. For the turbine, ideally you want more, so that's why they're flipped. The efficiency is defined differently. And then this is going to be the delta H. Again, it doesn't really matter the order, but we can do, I guess, exit minus inlet, so 2 minus 1. So H2S minus H1. Sorry. H2S minus H1 divided by H2 minus H1. So now I can find the enthalpy at the pump exit. And I guess I shouldn't have called it 2 and 1, I should have called it 4 and 3. So let me write that. H4S minus H3 over H4 minus H. So this is the state 4. And that's what's asked for here. So if you do that, you'll get the enthalpy at the pump exit. Determine the power produced by the turbine. That would be right here, right? H1 minus H2 times mass flow rate. That'd be for the turbine. And the work for the pump, I'm assuming that's the next question. I'm not sure, but M dot times H4 minus H3. Now, it depends if I wanted to answer negative, but usually I usually view pump power as positive even though it's work in, right? But, so here I said a positive number. So the power required by the pump. So I'll give that as a positive number. And then determine the rate of heat transfer to the boiler. That's just the difference between state 1 and state 4. So Q for the boiler equals M dot. So this is from 4 to 1 times H1 minus H4. That's how much energy is going in to raise the enthalpy. And that's right here. And then finally, the thermal efficiency is simply the thermal efficiency for the plant equals the power for the turbine minus the power for the pump divided by Qn, which is Q4 to 1. So this is a basic Rankine power plant, but with isentropic efficiencies. And this is the hardest one of the next homework set. So the other ones, there's just no There's no isotropic efficiency in the turbine or the pump, so those go really fast. The first one, the very first problem, is just a Carnot problem where these are the four states. So this is the inlet to the turbine, this is the exit to the turbine, this is the inlet to the pump, and the exit to the pump. The problem is that will tear up your turbine, and a pump can't take saturated liquid vapor mixture. So it's impractical, but it does represent a theoretical maximum for if these are my operating temperature, because the Carnot cycle is a reversible cycle. So it helps us, I guess, make a connection between what's the difference between the Rankine and the Carnot. The only problem with this one is this is my maximum temperature. So I need to do a Carnot cycle that's like that, and that's tough to do with saturation curve in there and stuff. But anyway, the efficiency for the Carnot cycle is always going to give us a limit to any other power cycle. So, and anyway, the first problem, the Carnot efficiency. The maximum for this problem, the maximum possible efficiency would be 1 minus T cold over T hot. So whatever this highest temperature is in this problem and the lowest temperature in this problem, the efficiency I get when I do the Rankine cycle better be less than that. Right? So that's kind of a reality check. Or if it's a multiple choice question, you could do that real quick without even doing any of the details of the problem. And if there's only one value lower than that, then that's the one you pick, right? So just a quick double check, especially for your project. Any questions?
For the efficiency part, we use the enthalpies.
This one?
No. The efficiency of the pump, both the ideal work or the actual work.
This one.
Yes. You're doing, if you had the temperatures at 4 and at 3, could you just use the temperatures instead of the enthalpies?
Okay, so the question is, do you have to use the enthalpies? You could get an approximate answer with just the temperatures if you said the specific heats are constant. So it wouldn't be a bad answer. So what you would replace is delta H could be replaced with Cp delta T or C delta T, since the liquid is just C. So if you said, what's the specific heat of water? And then, well, couldn't this just be the temperature change? You could do that. I guess the problem, well, you get an approximate answer. This specific heat does change, depends how much those irreversibilities, like how much that would actually raise the enthalpy versus the temperature. It's probably not going to change it much, so you're probably pretty safe doing that. But that's another way to do it. Then you got to go back though to an enthalpy at the end, because we want the enthalpy in the, well, I guess you could use that just for pump work though.
Yeah. But it doesn't apply to air case, or does it? 'Cause for the air compressor, in the first one, I did the temperatures, and it gave me the right answer.
Yeah, it depends. So
Just
Cp delta T, so again, the question being asked here, just probably can't hear it. So when does, so like for an ideal gas, delta H equals Cp delta T. That's a good assumption for ideal gas where the temperature doesn't change a lot. So for the compressor, yes, that could work if there's not a really big temperature difference, or I'm allowing some tolerance on the answer. But strictly speaking, that's an assumption that's not as accurate as that. If Cp is a function of temperature, then you're going to have some error introduced there. Now, sometimes you can use like the average specific heat if you know what the final temperature is going to be, and then you can use that specific heat in that average range. So you can get away from using the tables, and we do that a lot of times. When we look at some other problems, we're going to make those assumptions. It just makes the problem solution a lot faster. And then maybe at the end, after we've done a bunch of quick calculations, we want a really accurate answer. Then we go to the trouble of looking at tables and things. Yeah, occasionally that's an okay approach. I would make sure you're comfortable doing it both ways. And then if I say do not assume constant specific heats, then you know, okay, I can't click them. And sometimes they do say that in the problems. You know, use variable specific heats means don't assume constants. Okay, let me stop this one.